And particularly, the type of simulations people are doing, for example, in buffeting, is already used in design decisions, for example, by NASA. So NASA is dealing with, they're designing this space launch system, right? A lot of us know that. And but a few of us know that it encounters buffeting problems, the same kind of buffeting problems airplanes are under. Because the connection hardware between the main part and the solid rocket boosters, there is a shockwave sitting here, and there is also vortex shedding over the attachment hardware. So the unsteady flows just propagates downstream, and it turns out for the original design, there is a structural vibration frequency that overlaps with the frequency produced by the flow field, and it has buffeting problems. So NASA is doing, so first of all, you can't use rings to simulate this because it doesn't produce any frequencies. You can also use unsteady rings because although it gives you unsteadiness, the frequency content is totally wrong. You have to at least use the chaotic type of, they call it detached eddy simulation, to simulate that. And they are doing all kinds of things, but right now they are still based on a very empirical trial and error approach. And the same kind of high fidelity simulations is required for airplane buffeting simulations. So if you do unsteady rings, the frequency you produce is totally wrong. In gas turbine engine simulations, resolving this chaotic dynamics is even important for the mean dynamics. For example, if you're interested in heat transfer over the tail of a turbine blade, where there is a cooling flow coming out of slits like that, and you want to see how effective the cooling is, if you use unsteady rings, you are very vastly over-predicting the cooling effectiveness of the flow coming out. And the chaotic type of large eddy simulation is really necessary for you to do any engineering decisions based on this kind of simulations. Okay, so the current practice of doing this is really trial and error. So this is what NASA is doing. They try all kinds of nose shapes. They make the nose to be blunt, like on axis, canted, and things like that. And they run a simulation on each one to see which one works best. Of course it works, but it's a really, it's an approach that is really ad hoc and potentially misses a lot of opportunities for you to make more optimal designs. So NASA CFD 2030, which is a NASA report that has been produced a few years ago, says that the use of CFD in aerospace industry is severely limited by the inability to accurately and reliably predict turbulent flow with significant regions of separation, which is a lot of cases. And a lot of people are making this kind of simulations better and cheaper, and actually ZJ has made a lot of contribution towards that goal. And my goal is to see, can we perform sensitivity analysis for this kind of next generation aerospace simulations to enable a design process based on this kind of high fidelity simulations that resolves chaotic flow dynamics and allow you to efficiently explore many parameters and also perform error estimation and uncertainty quantification to this kind of simulations. And to overcome the deficiency of the ad hoc approach to design, I want to adopt what is the best in the class of traditional design tools, that is the Adjoint method. So the Adjoint method is a method that enables you to perform optimization very efficiently through differentiating the output of a simulation to its input, to many inputs simultaneously by tracing backwards through all the calculations involved in your simulation. I'm going to give an example. This is my simulation. It's a very small simulation, but if I choose a big simulation, the Adjoint process actually works exactly the same. This simulation has two inputs, x1 and x2, has one output, f, that depends on the inputs. And the calculations are just a sine, plus, and times. The Adjoint goes backwards, starts from the output, the last operation. It starts with the seed, that is the derivative of the output with respect to the product of the last operation. Well, because the product of the last operation is the output, so the derivative is 1, right? So the seed is always equal to 1. Then the next step is what's done millions of times in the adjoint calculation. That is taking partial derivatives of a single calculation. We already know the derivative of the output to the outcome of this plus. Now I want to look at what is the derivative of the same output to the ingredients or the inputs of this plus. Of course, we use the chain rule. The derivative to input is the derivative to the output times the partial derivative of this operation. In this case, for a plus operation, the partial derivative is also 1, right? So the derivative of f with respect to the inputs of this plus is also W5, which is 1 times 1. Okay, chain rule. Now I can go forward further and look at a differential, this multiplication. I know the derivative of f to the outcome of this multiplication already from just the last operation. Now I look at the derivative of f to the inputs of this multiplication. Now the partial derivative is a little bit more complex. It's the W3 adjoint times W1, which is the other ingredients of this multiplication. So the derivative with respect to the two inputs of the multiplication can be calculated. I can go also through this sign calculation also backwards to get the derivative of f to the inputs of the sign. And this way, I get the derivative of the same input with respect to both outputs with a single sweep, right, backwards through the calculation. And the process works no matter if I have 1 input, 2 inputs, or a million inputs. I always just need 1 sweep backwards through the calculation to compute the sensitivity with respect to all these inputs. That's the advantage of the adjoint method. You can perform sensitivity analysis with many inputs simultaneously with the same cost. And you can imagine my inputs can be something like this. This is a study NASA has done. And the inputs in this case is the entire shape of a supersonic airplane. The output is how loud this airplane sounds when you're on the ground. The simulation is pretty complex. You have to solve the flow equation near the airplane to get the pressure somewhere in the intermediate range. And then you have to solve the propagation of the sonic boom from near the airplane all the way to the ground. And then once you have the pressure signal on the ground, you have to transform it into frequency space and multiply that with the sensitivity of your human ear to different frequencies to get the perceived loudness. And the adjoint is just going backwards, first through the loudness calculation, then backwards through the sonic boom propagation, and then backwards through the CFD calculation to get this map. It's not a map that a regular engineer, even very experienced engineer, would be able to tell, right? You have to go through all these calculations to figure that out. And it tells the engineers where you should make the airplane thinner or thicker to make it quieter, right? Because, you know, for the red regions, if you increase the thickness of the airplane, it makes the sonic boom louder, sounds louder. If you make the blue portion thicker, it actually makes the sonic booms sound quieter. This kind of information is very useful for engineers. If you can have this adjoint field for the sonic booms, for the fuel consumption, right, for the lift, for all different things, it tells really well the engineers how I should change the shape of the airplane. And this is nowadays a lot of airplanes how it is actually designed.